Okay, today I'm going to do 4 or 5 demos, and then I'm also going to do a explanation of one of them. 3 of them, your job is to explain them on the prelim last class. Okay, so the first one is demo 1. Is the hoop demo. And this was prelim question number 6, 7. And what we had was a round hoop. Now there's a catastrophe here. My pendulum has disappeared. It's reappeared. Okay, you had on the prelim this question about calculating the period of oscillation of a round hoop. So the idea is that the hoop was swinging around. Somewhere there's a joint in this hoop which is heavier than the rest of the hoop, and I want to find that joint. Here it is. Okay, the hoop was swinging like this, and you're supposed to calculate its frequency of oscillation. And then the third part of the prelim was you're supposed to compare that to a point mass. So here's not quite a point mass, but the moment of inertia about the center of mass of a small thing is on the order of the mass times the radius squared. If the radius is small, the mass times the radius squared will be much bigger than your other terms in your equations, which is mass times distance squared. So if this is like a 20th of the size of this hoop, the moment of inertia about the center of this thing will make a contribution of about 1 part in 400 to the answer. So approximating as a point mass is reasonable. Right at the beginning of the semester, we just said they're point masses. Now we can calculate how accurate the approximation is. Okay, now the question is, if this swings back and forth like this, how does that frequency or period of oscillation compare to this one swinging back and forth? You see, well, this one swings faster. And that what length do I pick to get them to match? And if you did the prelim calculation correctly, it said that to get the periods to match, you should get the length of this pendulum to match the diameter of this hoop. So if what we're teaching you is any good, it should be that these two things swing with about the same period. Can you see that with back in TV land? Okay, we want to compare the period of oscillation of the point mass with the pendulum, and I swing it by moving my hand, which now somehow I excite it by moving my hand. That's accelerating the support point, and at this point you know how to calculate the motion if the support point is accelerated too, and the equations of motion for the simple pendulum and the hoop should be about the same, even for that. And if you doubt that, you think I cheated, let's just make the length here a little bit wrong and then see how it works out. Now I try and swing them together. It doesn't work out. Okay, any questions about this demonstration? Or how it relates to the prelim question that you're supposed to totally master it in your redo that you're doing that you're going to hand in a week from today? If I do it too long. And then I excite it by accelerating this point here. Move slower. But if I get it just right, and I excite it by moving the support point, they both have the same equations of motion, so they move together. Any questions about this? So at the beginning of the semester, I said this course is not that useful. I didn't mean it doesn't describe real things. What I meant is that when you go to do dynamics calculations engineering, they're usually not this simple, and we don't take you far enough to do most problems that are useful for engineering. Totally clear? Did somebody say something, make a comment, make a question? Yes? The prelim question first said, what's the period of oscillation? What's the equations of motion? What's the period of oscillation? And then it said, what would the length of a simple pendulum be so that it would have the same period of oscillation? And the answer comes out to be the diameter of the hoop. And we could have done an experiment and got the result. Wouldn't have had to do all that calculation. Okay. By the way, if you want a hula hoop, I think you can still buy them. They were really a big craze. When I was 5 years old, it was like a big craze. Like Pac-Man is too old for you. Like, I don't know. What's a big craze now? What? Pokemon? I don't know. Tetris? There's a revival of Tetris, isn't there? Anyway, if you want a good hula hoop, take this outdoor plumbing pipe and put a little plug of wood in. Then you get an adult hula hoop that I'm not going to show you, but I can barely do it even with this one. Okay, that's demo 1. Demo 2, we did in the class, and you did in homework, I believe, also, this problem of which way does this spool go if I pull on this film and it goes towards me. A different question, I need somebody to catch this. It's what happens if I put this on a ramp, I hold the spool still, and I let this fall. You can catch it on top. You don't have to let it fall off the table. I'd stand up. Do a whole block there. Okay. Okay? Now what happened there, almost all of you got this wrong. The vast majority of you got this wrong. The question is, how do we deal with friction? It's sliding. Well, is the bottom of this thing sliding this way, or is it sliding this way? It's sliding up, which almost all of you got wrong. How can you see that, though, just quickly, is this point right here has 0 velocity. This is a rigid object. All the points on this are going in circles around this point instantaneously. So if this has 0 velocity, relative to this point, this thing is rotating like this. And this bottom point there, or is going uphill. Is that clear? To make it more clear, let me exaggerate. No, you don't get off so easy. You volunteer for the Army, you're stuck for 2 years. What? That's why I'm in college. That's why you're in college. To make it more clear, here's a hoop that has a smaller radius. So you can't see it on the inside, but the radius of this thing is less than the radius of that other one. And if this slid down the ramp, which it doesn't, because you have to lift this up, or you have to hold, you don't want to lift or you want to hold? Lift. If this is, I put this has extra high friction tires because it was made for the spool demo that we already did. Yeah, you want to lift that until this slides. It's heavy, just warning you. More. What's going on here? Okay. Be careful. Okay, if it's steep enough, it will eventually slide. Okay, it's not very well centered, but you see, okay, it slides down the ramp. This one is pretty clear which way the sliding is, right? Just hold it there. I'm not going to exaggerate it. I'm going to force it. I don't want to exaggerate it because I want you to get the kinematics right. So when it slides down this thing, it goes like this. This is the motion. And that big spool is doing the same thing. It's just that because the inner radius is close to the outer radius, the motion at the bottom is less, but it's still sliding uphill. Any questions about that? If you have doubts about it, you can make something like this with cardboard, string, toilet roll. You can make demos of these things quick. In half an hour, you can do these experiments in your dorm room. Any questions? Okay. That's demo 2. We're done. We can go all the way down now. Okay. Okay. So there's spool demo. And that was P8. Then last was the arrow. And a bunch of you had trouble with this one also. What did I do with my arrows? It's tough being senile and teaching at the same time. You can just refresh in your mind what the arrows were. Arrows. So there's a stick with a ping pong ball. I used a cotton ball instead. And the idea is, can you write the equations of motion for this? Equations of motion means given the position and the velocity, can you find the angular acceleration and the total acceleration? And the idea is the stick glides through the air easily, and the cotton ball, ping pong ball, does not. You'd like to think it was an arrow, so it should go straight. But if you assume it goes straight, that violates the laws of mechanics. So it's a bad assumption. It's going some crazy way, and maybe eventually kind of ends up straight. So if I throw it sideways, it kind of tends to go straight. Now, that's what you were supposed to figure out. What was the slightly tricky part about this problem is you have to calculate the velocity of this point in terms of the velocity of the center and the angular rate. Given that, you know the force on this point. Given that, you can calculate the acceleration and angular acceleration. Now, the same thing goes here, where we put feathers in the back, but the feathers cut through the air and just have sideways friction. And this is a much better idea for an arrow. If I throw this sideways, what happens to it? It ends up getting straight much better, much faster. You want to compare? Let's see. Compare the two, scientific experiment. Not so clear, but the feathers work better. Why do the feathers work better? If you want to really reason it out, do a MATLAB simulation. Not so hard. You've already got the equations of motion. But the friction force here has a big moment arm, the air friction, because it's perpendicular, whereas this friction force is resisting the motion, and when it's nearly straight, it has a small moment arm. So this one is much better at straightening this thing out than just this friction. And this one slows it down too, so it's twice over bad. Okay. So that's the arrow demo. Any questions about that demo, the question, the calculation, anything like that? Okay, then last is the bike demo. So this is my bicycle. I need a, you're the guy who said you'd do anything, right? I can't say it's not a special bicycle. It's my special bicycle, but it's not specially made for this demo. The demo I'm going to show you would work with any bicycle. So if you're after this demo is done, you don't even have to have a bicycle. You can just go to the bike rack and you can do this demo even with a locked bicycle. Okay, so what I want you to do is just balance this so delicately that it's quite clear to everybody that you're not pushing the bicycle forwards or backwards. Okay. Now what I'm going to do is tie a string to the pedal here. And I'm going to pull backwards on this string, on this pedal. Let's see. I'm blocking the action, but it's not a trick knot. Okay, in fact, I'm not even going to do it. Michelle is going to do it. Okay, now, don't do it yet. She's going to pull gently on that string. What's your name? Julian. Julian is going to gently balance the bicycle, and the bicycle is going to either stay still or go to the left or go to the right. Okay, now sit down, then you're going to get back up again. Okay. Okay. No talking. Hey, just raise your hands if you've seen this puzzle before. Just where did you see it, out of curiosity? High school. Okay. 5 seconds left to vote. Is the votes recording? 4. Any questions about the question? 3. Oh. What are you, in theater also? Are you in theater also? Okay. Right is your right. As opposed to the right screen on this button, which is that way. Ignore what I just said. Okay. That way is right. That way. Right. Any other questions? Okay, we lock up the vote. Did I succeed in turning off the vote? Okay, let's see how you guys did. Right, left, stay still, D. Okay, Michelle. Balance very gently. Pull gently. Okay, you want to set it up again? Balance gently, pull gently. Okay, does anybody want me to change anything about the bicycle? Now, it's not a trick. You go and do this experiment yourself, you will get the same result. I didn't do anything fancy here. You do it with any bike, you'll get the result. Okay, so it goes left. I managed to fool the majority of you, but I don't win unless I get less than 20% correct. Okay. Now the why of it. Anybody think they know the why of it? Yes? Okay, so he says I apply a force here that has a torque here that causes the same torque here, which is related to a force here. So the propulsive force in the bicycle comes from this torque, but there's a bigger lever arm here. This force is smaller than this force. Therefore, the net force is backwards, he says. Okay, that argument actually is 100% correct, so long as this sprocket radius, this is called the front one is called the front sprocket radius, is equal to the rear cluster radius, which it almost is the way I've set this up. But if I change the gears, I still get the result. So the result is not dependent on that gear ratio. Can you turn the pedal, please? Turn the pedal around so I can change gears. Yes, thank you. Let me change them substantially. Oops, that's the bell, not the gear. Okay, so now we do the demo again, and now the radiuses aren't the way you said. Now do the demo again, please. Okay, now what's the explanation? Yes? No, but let's draw a free body diagram of this bicycle in our heads, please. How many forces are there? There's this force, and there's also a ground reaction force. So it's F equals ma. But you have to know the sizes of the forces. Okay, so there are a couple ways to reason this out. One is exactly the way this guy did, but now the reasoning isn't that this torque, the torque on this wheel from the chain is equal to the torque on this wheel from this chain. It's that we can calculate them. So if we know what this force is, we can calculate this chain tension by knowing this radius and this radius. If we know this chain tension, we can calculate the reaction force on this wheel by knowing these two radii and the size of the wheel. Calculation is especially easy if we assume that the wheel and the crank have low enough mass so we can do statics calculations on these parts, even though the overall calculation is a dynamics calculation. Wheel has negligible mass, crank has negligible mass, bike, right here on the seat, this big fat guy with the beard and teaches mechanics. Okay, so there's a negligible mass here and big mass here, and we can calculate the force by doing all these statics problems. The claim is that for any real bicycle, this force is smaller than this force. And you get that answer if you assume this wheel has the same radius as this one, but this radius is smaller than the wheel radius. Or if you take any of the geometry of any real bicycle, you get that answer. You can make a bicycle where this is not true. If I took this sprocket and made it gigantic, so that the ratio of these two radii was smaller than the ratio of this radius to this radius, then the bicycle will go forwards. But there's no bicycle you can buy with gears that are that low. Okay, now here's a different way of thinking about this problem. Why do you ride a bicycle instead of walking? It's because you go faster. What do you mean you go faster? Well, you move your feet around when you walk, you move your feet around when you bicycle, but the idea is that for a given sort of motion of your feet, you go faster on the bicycle. Part of the motion of your feet is going backwards relative to your body. And the whole idea of a bicycle is that when you move your feet backwards relative to your body, your forward speed is even bigger than that. When you walk, can you hold it? When you walk, your downwards foot is going backwards relative to your body, but that's exactly the speed that your body is going forwards relative to the ground. When you're biking, your foot is going backwards relative to your body, and you're going faster than that. That's what's so nice about bikes, right? You move your feet that same gentle way. It's not exactly a walking motion, but you go fast. That means you're going faster than your feet are going backwards relative to you. That means the pedal is going forward. So in normal bike riding, the gears are set up so that when the bike goes forwards, the pedal is going forwards also. When the bike goes forwards, the pedal is going backwards relative to the bike, but absolutely forwards. If that wasn't so, it wouldn't be fun to ride a bike. Your feet would be spinning around like crazy, and you'd rather walk. Which is true. If you get even on a mountain bike with very low gears, your feet move too fast, and you don't like it. Now, they don't move as fast backwards relative to you as they would if you're walking, but they still move too fast. You don't like it. You like it with your feet going slowly relative to you on the bike, which means they're going forwards relative to the ground. So you see, when the bike goes forward, the pedal goes forwards. Is that clear? So the gearing on a bike is such that when the bike goes forwards, the bottom pedal goes forwards. Any questions about that? Do you want to nudge her and ask her if she's sleeping or thinking deeply? Or both? That's what usually happens to me. It's like I go to a talk and I think it's really interesting. I go, that's really interesting. And I go, oh, yeah. I also do the same thing if it's really boring. Oh, that's really boring. Okay, so this is how it works. But that means the gearing, if the gearing is like that, that means when a bike goes backwards, the pedal goes backwards. So the gearing on bicycles is so that the bottom pedal goes the same direction that a bike goes. Now what you know in this experiment, balance this again please, is that when she pulls on this, she does work. If she does work, that means the force she applies, which is in that direction, has to be in the same direction as the motion of the pedal. So when she pulls on the pedal has to go with her. But the gearing on a bike is such that when a bike goes forward, the pedal goes forwards. When a bike goes backwards, the pedal goes backwards. Her pulling on the pedal and putting work in means the pedal has to go backwards, which means the bike has to go backwards. So without doing all those detailed calculations about gear ratio, but just knowing the nature of a bike is that it makes it easier to go forwards, means the nature of a bike is that the pedal goes forwards when the bike goes forwards, the pedal goes backwards when the bike goes forwards. For her to do positive work, the pedal has to go backwards. Therefore, the bike has to go backwards. Yes? It makes a difference, but we don't get the sign change here because this problem doesn't have in it that geometry where the moment about the contact point switches sign depending on the angle. So if I do the detailed calculation, all the details are different at the different angles, but actually the most favorable thing for going, no, that's not even true. We get a sign change here. Cancel that. Yes, it does make a difference. Ready? If I pull up, balance carefully, and there's some critical angle somewhere in here, close to vertical, because the gearing is so high here that it, just there, doesn't know which way to go. Here it goes forwards, here it goes backwards. So yes, take it all back. Does depend on the angle. Does that answer your question? You're right, I'm wrong.
That angle determined by the gear ratio?
Yes. So let's now do the calculation. I'll be back tomorrow. Okay. Okay, so the setup for this question is we have a bicycle. Any questions about the picture? So we could draw a free body diagram of the bicycle. And the free body diagram of the bicycle, we don't have to draw all the details quite so well. But it's got a force here and a force here. Any other forces? Okay, there's vertical forces, but we're going to do the one-dimensional mechanics of this thing. Did I leave anything out of that free body diagram? How is this free body diagram different than the free body diagram I would draw if I was doing the problem of me riding my bicycle? What would change in that free body diagram? Shh. What would be different if, instead of doing the problem in the lecture demo, I was doing the problem of me riding my bicycle? What would change in this free body diagram? Who has an answer in their head? Raise your hand. Who does not? Raise your hand if you have an answer in your head. Hi, 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 hi. Do you have an answer in your head? You didn't raise your hand when I said does not. You either do or do not. You do. Okay, then you have to participate. Otherwise, the whole group dynamic doesn't work. Okay, you got 3 days to learn that. Okay, what's the difference? Not you, you already tried. Anybody tell me what's the difference? Go ahead. Yeah. The force in the pedal will be in the other direction. Why do you say that? I'm riding on my bike and I'm pushing back with my pedal. Hey, another idea. Yes?
Push down pedals when you ride the bike.
But this one, in this position, you don't, pushing down doesn't really do anything. So if you're really trying to ride a bike,
You don't push on the pedals in that position when you ride a bike.
yes, you do sometimes. It's not the main part of the power and propulsion, but for example, if I get on my bike in that position, I can make it go. And they call it spinning, and the people use it when they go in very low gears. Yes. Okay, so the question is this a free body diagram of the bike or the bike and the rider? Let's say it's the bike and the rider. Yes?
Have more weight on the bike,
There's the weight on the bike.
which rider, and then
It's bigger. Okay, so now the arrow gets bigger.
possibly if you're pedal, you might also be pushing forward.
Pushing forwards on this pedal. That could be, but maybe not. Yeah?
I was going to say there's no force in the pedal.
Absolutely. It's a free body diagram. You go up to the bicycle and the rider, and you go up with a chainsaw, and you cut it free from the world. As you cut it free, you pretend, I'm the chainsaw massacre, and I'm going to get away with this. So I'm going to cut it free, and I'm going to get away with it because I'm going to fool it every place I make a cut. I'm riding this bicycle. You're trying to do an analysis of me on this bicycle. You cut me free from what? My Mother Earth. Okay, so you put a gravity force down. You cut me free from the ground. You got to fool it. You put an upwards force in the front wheel, not a frictional force because it's a good massless ideal front wheel. You cut it free from the ground in the back wheel. There's a vertical force and a propulsive force. Did you cut me free from the pedal? No, you're drawing a free body diagram of me and the bike. There's no, your chainsaw massacre didn't go there. There's no fooling to do there. You just cross off the force at the pedal. Okay, free body diagram, very powerful concept. Now, which way does the bike go if I push back on the pedal? By a different analysis of the internal parts, we could figure out that this thing was positive, and the bike goes that way. That's why you ride a bike. Bikes go that way when you pedal them. Okay, but this is not the problem we're doing. We're doing the problem with Michelle on the outside pulling on this thing like so. Okay, now we want to do an analysis of this system. How are we going to do an analysis? Well, we've got to label dimensions and forces and stuff like that. Okay, so what dimensions do we have to deal with here? Is we have, say, the length of this piece here. This is called the crank on a bicycle, the one that connects this crank axle to the pedal. So that's the length of the crank. And then we have here, this is called the radius of this front sprocket, so I'll call it the front sprocket. And then I've got the radius of this thing back here, and this is called the rear cluster, so I'll call it R cluster. Does anybody have a better name for any of these things? Any bike riders here? Yeah? What? Very good. Cluster, cassette. Very good. And then we have the radius of this wheel here, and this is the radius of the wheel. And these are all the dimensions we need. We've got this mass here, and we'll neglect the mass of the wheel and the crank. Now, if we did the analysis the energy way, where I said Michelle does positive work, therefore the pedal has to go that direction, it would be easy to incorporate the inertia of the crank and the wheel. But it wouldn't change the answer very much. It would be a quantitative change. If we do this whole detailed dynamics, it makes it a bit more complicated, so I would like to skip that. So I'm going to do statics of the parts. And by the way, this is why statics is generally more useful than dynamics, is because when you go to do any real dynamics problem, like an airplane in flight, the big loads, the dynamic loads, are one part of the problem, but all the rest of the structure is more or less a statics analysis as loaded by these dynamics loads. So in the car team, you look at a strut, you look at the loads on that strut, you do a statics analysis, for example. Okay, so now we want to break this apart, and we want to do free body diagrams of the parts. So what parts do we have to deal with? Well, we've got this part with the pedal on it, and then we have to deal with this thing here, which I'll call the force of the pedal. So here was that arrow there is the force of the pedal, and this is the force of the ground. And I'm not going to really need other quantities here. So here's the force of the pedal. So I broke this free from the foot. I'm going to break this free from the axle on the bicycle. I'm going to break it free from this chain. So I'm going to cut the chain, and I'm going to show a force here which is not part of the chain. It's the force on the chain, which I'll call the tension in the chain. And that's my free body diagram of that part of the bicycle. And if I need dimensions here, I have here what I called R of the front, what did I call that, L? No, this one was called RS, R of the sprocket. And then I also have here this L of the crank. Okay, so with this thing, I'll just do my moment balance, sum of moments relative to C is going to equal to 0, because I'm going to do a statics analysis, and I'll call this point C for the crank axle. And that tells me that the tension is equal to the force on the pedal times the length of the crank divided by the radius of that sprocket. Now I can draw a free body diagram of the, this is of the crank assembly. I can do the rear wheel. And the rear wheel looks like this, and it looks like this. And I have to cut it free. I cut it free from this chain, and I show separate from the chain the force on the chain that I took to fool the chain into thinking it was not cut, which is that tension. Then there's some reaction forces here, and then I'll call this point D, and there's a force here, and then there's a force here, which is the one I care about, the force of the ground on the rear wheel. These ones aren't going to enter my calculation because I'm going to do the sum of moments relative to point D and set it equal to 0. Statics calculation. I could do a dynamics calculation. You should be able to do a dynamics calculation. It's just extra clutter in this problem because those masses are so small, they change the answer such a little bit. Just like in this pendulum problem, I could have taken into account the moment of inertia of this mass, but if it's so small, you neglect small terms rather than include them and say they're small and go through lots of algebra to get rid of a term, and then get rid of a term because it's so small. Just get rid of it ahead of time if you know it's small. If we do this calculation, we get that the force on the ground is equal to the tension multiplied by this radius ratio, which is the radius of that rear cluster divided by the, was that a small r or capital R, the radius of the wheel. But that, in turn, is equal to the tension we've got over here is this force on the pedal. So we get the force on the pedal multiplied by this RC over RW, and then it also gets multiplied by LC over RS. And then the whole issue here, when we go back to drawing the free body diagram of the whole bike, so we'll use linear momentum balance for the whole bike. Whole bike. That says that the sum of forces on the whole bike is equal to the total mass times the acceleration of the bike. We'll assume the acceleration of the bike is in the I direction, and we're leaving off the mass of the, we're not worrying about the rotation of the wheels. What do we get from this thing is we get that there's a force of the wheel on I call that force of the ground, pushing forwards, and we have minus the force in the pedal, pushing backwards, equals the mass times the acceleration of the bike in the I direction. Okay, so if we take this equation, the other one, and dot it with I, this is what we get. Okay, so it says then that the acceleration of the bike is equal to the force of the ground minus the force of the pedal divided by the total mass. But the force of the pedal was common to both factors, so we get the force of the pedal multiplied by this whole cluster of terms, LC RC over RR, LC RC over R sprocket, and we had R wheel, minus 1, all divided by M. So the result we get is if LC RC over RS RW is greater than 1, that implies the bike goes or accelerates right. And if that quantity is less than 1, the bike accelerates left. Okay, so you copy the stuff on the board, ask questions about it, and then I'll make a comment or two about it. Just as you're looking at it, something is unclear. You think something is unclear, something is wrong, something doesn't make sense. If I got hit by a truck and you had to do this problem yourself, you couldn't do it because of X. Tell me what X is. If you don't like the truck metaphor, make up another one. Hopefully less gruesome. Yes?
If the quantity is greater than 1, the bike moves with that.
Yeah, so if that quantity is bigger than 1, that corresponds to a very low gear ratio, what's called a low gear ratio. Low gear ratio means that there's lots of pedal motion for little wheel motion, and the bike would go forwards. That whole quantity, the meaning of that whole quantity, by the way, is the ratio of this velocity relative to the frame to this velocity relative to the frame. And that's what you're talking about, whether the whole thing is gearing up or gearing down. So if that quantity is bigger than 1, it means this quantity, this motion is smaller than this motion, and this force is bigger than this force. And the ratio of these forces is exactly the ratio of the motions, just like with a lever or a pulley system, because this mechanism on the whole has to balance energy if you move it a little bit when forces are applied to it. So this force times this displacement has to match this force times this displacement. Yes? Say again? Doesn't depend on friction. So implicit in this problem is that the friction is high enough so this rolls without slip.
Is there any point in which you have enough normal force that you could, like, even 5 going backwards,
What, Julian, please? Can you balance this gently here? Okay. What?
I'm not sure which one that was.
He said if I pull it hard, does it actually go backwards instead of forwards?
No, if you put enough
That was
That seems like
You were asking about friction. I said we made the assumption that it rolls without slip. If we pull it hard, we violate that assumption. What's your question?
if you add enough normal
Yeah?
Is there a point where you push out hard enough to go move forward instead of back?
Push down on the seat?
Yeah.
I don't see that anywhere on these free body diagrams or anywhere. No. A guy like me wishes a thing like that was true. It's just the same way I'm like looking for that ice cream, that the more you eat of it, the more weight you lose. Haven't found it yet. Okay. I've fallen off this bike lots of times, don't worry about it. Yes, any other questions? Everybody got everything copied down? Okay, what about, can we actually untangle this? This looks like a big mess. Can we untangle that mess? Well, it's got one ratio in it, which is the ratio of this to this. What was that? That's the ratio of L crank to R sprocket. So that tells you how much this chain tension is getting big. And then we have another ratio in it, which is this R of the cluster to the rear of the wheel. And that tells you how much we're losing of that force down here. So if you look at the ratio of these ratios, you'll see on any real bicycle, we get that this goes to the right. Some imagined fake bicycle where the crank is very long, one way we could do that is we could tie a stick to this crank and make the crank very long here and stick it below the table. Or we could put a giant sprocket up here, or we could put a teeny sprocket up here. Then the bicycle would go forwards when we pulled backwards on the pedal. Okay, any questions about this question? We have 2 minutes left in class. We could say, I owe you 2 minutes over the semester, or you could take advantage of this opportunity and ask me that deep, important question, which is going to give you all the insight you want. Okay, so I'll give you 15 seconds to ask a question about absolutely anything, and if you don't ask a question, then we'll let the class go. There has to be something that you're curious about that you think that I might know. I'm a little bit disappointed, but I give you back the minute I owe you from the semester. See you next time.